on, oh yeah, no, wait. Let me check again. Nope. That's getting recorded. So I thought, I was very conflicted on whether I should do some basic fundas or not. Then I thought with this group of August engineers, oh yeah, I think I can do it, hopefully. Now. Yeah, I can do it. Let me share. Can you see this?
Yes, we can.
Yeah. We can see your slides now.
Wait, I have some other shit here which I need to get rid of. Yeah. So there's a movie theme running through this presentation also that you guys can figure out. But this is from a movie from 1990. So hardware, you can't stop progress. That's the motto. Okay, so the outline of today's talk was, I want to start with the silicon ecosystem because we say chips, but it's a full ecosystem. So, and when we talk about things like what should be made in India and stuff, it's important to understand that there are many pieces. So spend a few minutes on that, spend a few minutes on the fundas of circuits and how you make circuits. And then we get into the interesting topic. So the fundas part may be slightly boring and intense, but I think you need to have a basic understanding to talk about topics like scaling, business models, GPU, China, and future trends. And then what would a talk be without a quiz? And especially at IIT. So we'll have a little quiz at the end of it. And then I have some additional material you guys can look at. And then there are yellow boxes all through the talk. These are trivia, random bits of information that I find interesting, but don't have really anything to contribute to the talk. So the ecosystem. Let me push this down also, this blocking here. Why is this? Is this blocking? Can you guys see this little thing blocking or no?
What do you mean? I mean, I can see that.
The slide is fine.
Okay, the slide is fine. Great.
Yeah, slide is fine. A small dot there. That's all. Nothing else.
Guys, everybody, please mute yourself. Only Vas and Gopal will talk for the time being until it is over.
So the way this whole ecosystem starts is with some company or some engineer trying to do design. So they have some idea to make a chip. And then what they do is they write code. Then this code is taken and EDA, which is electronic design automation or computer-aided design, converts that to a set of layers. These layers go to foundries. And foundries are the ones that actually build the chip. So the foundries buy equipment from a bunch of people. Here is Applied Materials, where our buddy Sesh works. And they also need material like gases and wafers. So they take all this, they take the design, and they build wafers. Now, these wafers go to other companies, which are called back-end companies. Amcor is a famous one. What they do is they cut this wafer into little die, and they put it in a plastic package. And these packages then go to system builders, like Foxconn is a famous name, which they're doing a lot in India, or people like Boeing or Lockheed or whoever. They take these chips and build systems which we interact with, like cars or cell phones. And these yellow numbers represent the amount of ICs, these chips, which are sitting in each of these systems. So like a typical car today has about 1,500 chips in it. So you can imagine when we had this COVID problem, why there was a problem manufacturing cars, because we can't get chips and lots of them, you can't make cars. So that's, and I've put in a lot of names here. So later on, when you're looking at it and somebody says we are setting up something in India, you can look at this and say, which part of the chain are they working in? So when there's a lot of talk of Foxconn, so you can see Foxconn is at the end of the chain. Or when we are talking of this foundries, and Pankaj said today about Micron, setting up a foundry. So that comes here, and we'll talk more about Micron and stuff. You can see Micron designs their chips and manufactures it, right? So it's a difference from, say, NVIDIA. But we'll get into that more. And this, I don't think you guys need this, but this is to explain to people how building a chip is writing a book, right? So then this is some miscellaneous information you need for the rest of the talk. The first is a pro forma thing which shows where we are. What does 2 nanometer mean? But I find this fairly useless, but I put it there because every talk must have this. Because I don't know what is the size of a DNA diameter, right? I don't have a physical feel, nor do I have a physical feel for what is 2 nanometers. A nanometer is 10 to the power minus 9 microns. So that's one thing. And then a gigahertz is 10 to the power 9 cycles per second. Again, that's 1 nanosecond. We'll be dealing a lot with capacitors. So for people who have forgotten what capacitors are, basically they're 2 plates with an insulator in between. So if you put a plus voltage on one side, it gets plus charge. The other side gets negative charge, right? Simple things. And you have CPU, which is the central processing unit, and GPU, which is graphics processing unit. So these are basic stuff that I'll be using, and just wanted to put it out there. And there are many types of ICs or integrated circuits or chips. There are many types of integrated circuits or chips. In today's talk, we're only going to focus on computers and compute chips, which are logic and memory. We'll get into that. But I just want to point out that a lot of other chips like power and RF, radio. So power is like for all your cars or motors. So on the right-hand side, high-speed rail, light industry, electric vehicles, or microwave ovens, all these use power ICs, which we're not going to discuss today. Then in your cell phone and stuff where you have, when you make a phone call and stuff like that, you use radio frequency. So there's a whole set of radio frequency ICs. Again, we will not cover that today, right? But I just wanted you to be aware that there are many more ICs than what we are going to talk. And so first topic is circuits. And so this is a review of what Pons said. This is the famous von Neumann architecture. And so how does, when you shut off your, turn on your computer, the only place that has information stored is your hard drive or your flash. So the first thing that happens when you turn your computer on is all your programs get moved from flash to memory. And then the processor starts executing stuff from memory, one instruction at a time. So there are fundamentally 2 sets of chips. These are called logic chips, which deal with the CPU, and then there are memory chips, which store data. And when you shut off power, it's only your hard drive that stores data or your flash. Your memory loses all information, and your CPU loses all information. And one thing we're going to be talking about today is how to make these smaller and smaller, the CPU and memory. But the main problem we have in computers is your input and output, because you deal with humans and we have fat fingers. So we still don't have a very efficient way to scale input. Audio is one way of doing it, but you don't have a good way of scaling the input or the output, right? You need big screens or you need glasses. So both of these are kind of inconvenient and prevent us from making things really small. CPU circuits, some basics. The basic idea is a switch. So here, if you put a voltage, you press the switch, the lamp turns on. Now, if you want to do an AND function, which is you put 2 switches like this, now both switch A has to be closed and switch B has to be closed for the lamp to turn on, right? So this is an AND function. Now, if you look at this function, you have 2 switches in parallel. So if I press either switch A or switch B, the lamp will turn on. So this is called as an OR gate. So now looking at this, all your CPUs are built of circuits like this. And if you understand how to press a switch, technically you could build this computer, which was in 1950, which was made of these switches or relays. Only problem was it weighed 9,000 pounds and it burned 3.5 kilowatts and it ran at 1 hertz, right? So that is the basics of circuit design, and that's enough for us right now. Now, when you
Gopal,
come to memory,
to complete the story, how would you, in the schematic, could you show how to do a NOT?
a NOT is a good question. The NOT, I would have to use a different circuit. I had it, I changed it. Okay, but one way to do a NOT is to, I need 2 switches for it. Okay, I didn't want to make it complicated, so I left out that piece of it. But I can show you at the end. Okay. So memory circuits. So the trick here is you have one capacitor and you have one whole address row. So you take an address and all the address rows connected to the switch, and the output is down here. So if there is charge on the capacitor and you connect the switch, each of these bits will read out the value of the capacitor, right? So if it's a 0 or a 1, you'll get a 0 or a 1. And now you have a lot of bits in parallel. So you turn this on, which is pressing all these switches in parallel, and you get, let's say, 1,000 bits out values from here. So the main thing to understand about these memory circuits is they have no intelligence in it, right? So all they have is ones or zeros. So they don't know it's a program, they don't know it's data or whatever. All that knowledge is there in the CPU and how it interprets this data. But the main focus of the memory circuits is to get as much data in there as possible efficiently. So you can see this is extremely efficient because it requires one switch and one capacitor per bit. If I tried to do this in the logic case, it would take me about 8 transistors, 6 or 8 transistors. So this is very efficient. It's got some problems. We'll talk about that later. And now talking about memory, one of the things that happens is, remember we said everything, all our data sits in flash or hard disk. But we have the CPU here, which runs very fast. So if I have to get data from hard disk, it takes a long time. So you remember how the program, I go get one instruction, execute it. So I execute the instruction very fast, but to get the next instruction takes me a very long time if I was coming from hard disk. It's further away from the CPU physically, plus it's slow. But the good news is it can store a lot of data, right? So what people have done is they move data from hard disk to memory, which is much faster than the hard disk, but capacity is lower. Then what they do is they put some more memory right next to the CPU. This memory is faster, is much faster, but it's much larger. So you can't put a lot of this memory. So what happens is data comes from the CPU, from the hard drive, gets put onto main memory, and then from main memory, you bring it close by, and then you deal with it close. So for example, if I ran everything from main memory, it would take about 200 cycles per instruction. So my CPU is sleeping for 200 cycles while it brings one instruction. Then it executes it, goes back to sleep, takes 200 cycles for the next instruction. So this is highly inefficient. So that's why we have these things called cache. So what you can do is the memory is pretty big. And you remember I told you can read 1,000 bits at a time or 10,000 bits at a time. It takes 200 cycles, but it produces 10,000 bits. So what you do is you load these 1,000 instructions into your cache. So the first instruction will take 200 cycles, but after that, the next 999 instructions will only take 2 cycles. So on an average, you'll end up running at 2 cycles instead of 200 cycles. So you got a 100x speed up. So if you look at processors, the way they look like is there's a core, there's an L1 cache, which is very close. Then they have a cache which is slightly further out because this cache is shared with multiple processors. And then you finally go to the RAM, which is sitting way out. Okay. So this is how processors are structured, with the logic, a little bit of memory next to the processor, with the main memory sitting way out. So when you buy a your laptop and it says I have 16 gig of RAM, that refers to main memory. The L1 cache and all, you don't usually see the specs for that unless you look at your processor more carefully. Once upon a time, this used to be seen in marketing literature, no longer. So this would be all in terms of gigabytes of how much gigabyte SRAM you have, and your processors would be how many gigahertz can you run the processor at. So next one is, so do you have any questions about the logic other than Vas's question, which I'll address later? Vas, were there any questions, or this was too intense?
Could you give a sense of scale? So for a modern laptop or iPhone,
Yeah.
how many components are we talking about? How many chips? How many units of memory and compute as well as the cycle at which things are running?
Okay, so let's say I take a cell phone. Your cell phone typically has about 128 gigabytes of flash or 256. That's storage. That's way down here. That's the flash drive. Then the main memory is somewhere in the 2 to 4 gigabyte range, right? Which is a factor of about, let's say, 50 less. And then the processor itself runs at about somewhere between 1 to 4 gig, probably even slower, 1 to 2 gig. And the level 1 caches are in the range of about kilobytes, right? So hundreds of kilobytes. Okay. So that's sort of what a cell phone looks like. So the ratios maintained when you go to a desktop, what you do is you really want a hard drive to get your 2 to 8 or 10 terabytes of data. Tera is 10 to the power 12 and giga is 10 to the power 9. And then what you do is you put a flash drive with about 500 gigabytes, because a flash drive is about 1,000 times faster than a hard drive. So again, if you think about it, what you want to do is you want to get the memory or the data as close to the processor as possible so that you can run fast. Otherwise, you're just waiting for data from memory. Okay. So next, how do you fabricate circuits? So now we come to transistors. So far, we were dealing with relays. We come to transistors. So how does a transistor work? Again, this is extremely low. So what a transistor has is it's got N and P in silicon. P means positive charge, N means negative charge. So when you have this, you cannot have current running from negative to positive to negative. Negative will go with negative or positive will go with positive. So you have a little capacitor here, and this is called the gate. So when there's no voltage on the gate, there's no charge, so no current. So it's like a switch which is open. Now, when I put a positive voltage on it, and remember, this is what I said about a capacitor. So you get positive charge here, you get negative charge here. Now you have a negative charge, which is connecting both the negative charge. So current starts flowing. And one of the important things which we won't go much into is, remember, when current is flowing here, this is where you generate most of the heat. And this heat has to be taken out by either flowing to the back or somewhere else, right? So that is a transistor. And you can see in 1971, Intel introduced the 4004, a chip which looked like this, which had 2,300 transistors. And remember, the relay ran at about 1 hertz. This ran at 760 kilohertz, so 760,000 times faster. And this size was 12 millimeters square compared to the huge box. So we made a huge step up or down in terms of size by going to a silicon transistor switch. So everything we talk about from now on, you understand how a switch-based logic works, and it's easy to imagine how you replace that switch with a transistor. And again, the function is the same. You put a voltage on, the switch turns on. You take the voltage off, the switch opens, and there's no current. Okay.
And this
Now,
is the first IC.
Pardon? Yeah, this is not the first IC. I'll show you some of the first ICs in later on. This was the first CPU. The story behind this is interesting. Intel got a contract from a Japanese watch manufacturer, calculator manufacturer. So they wanted a custom chip for a calculator. But Federico Faggini, who was one of the Intel designers, said, why are we building a specific chip for this company only for a calculator? Why don't we make a more general purpose chip, a CPU, and sell it, right? And these guys can do their stuff in software and other people can do it. So that was a major, major step. And that's how the first CPU came about, which was the 4004. And the 4 means it was a 4-bit CPU, right? So any register could count only up to 16, from 0 to 16. Okay, how do you build a chip? So the way a chip is built is a layer at a time. So what you do is a particular layer, you have a mask. And what you do is first you take your wafer, which is a flat piece of silicon, you put photosensitive material on it. This is like your film. You put a photosensitive film on it, then you shine light on it through the mask. So what happens is where the light shines, it becomes, it gets processed, so you can dissolve it.
Hemant, can you go on mute, please?
And where there is no light, the photoresist is what we call it, stays. So in step 1, you have a metal layer, let's say we want to pattern. You put photoresist on top, you put your mask, and you pass light on it. So wherever light went through, and then you you wash it away basically with some chemicals. So it opens up the photoresist. So now there are holes in the photoresist. And then what you do is you put acid or whatever you want to etch your metal. So the metal etches. And then what you do is you remove the photoresist and you got a pattern on the metal. What you drew out here on the mask gets transferred to the metal. So if we go back, you have many of these layers. So what I can do is I can put a metal connection from here to here on the next layer up. So what I do, I take this, I put some insulating material, open holes, put metal on top and pattern it. First, the metal will be all over the wafer. So then I have to cut it and pattern it to what I want to connect. Okay. And then what this is done is you do it for one chip on a wafer, then you move it by the size of the chip, and then you pattern the next die. Then you move it X and Y, pattern the next die. So finally, when you look at a chip, look at a wafer, each one of these is a chip, right? Each square, which has been patterned. So, but these processes like etching and photoresist are done across the full wafer. They don't do die by die. So you pattern it die by die, but the process that you do afterwards runs on the whole wafer. So that is the secret of making millions of die from a single wafer. Not millions, but overall, you can make, say, 5,000 die on a single wafer, one step at a time. So the patterning step is usually the long step because that has to be done one die at a time. But once the photoresist is patterned on the whole wafer, then the rest of the process, like dipping it, what you do is you dip it in a tub of acid, and that opens up the metal for all the die at the same time, right? So it's very efficient. So how does a chip fabrication work? This sort of is...
Gopal, a quick question. Die
Yeah.
by die, I guess it depends on the reticle and the die size, right? So if you're making tiny chips, it could actually, your reticle size could cover many die at the same time, no?
You could, but what is happening is as you go to smaller and smaller geometry, it's getting a large reticle size is harder. The other thing that happens is designers want to make bigger and bigger chips, right? So the size of the chip grows. So while in theory, yes, you can put multiple, but it was more popular in smaller geometries to put like
Okay,
4, 16 or whatever.
So die by die is the norm for steppers and stuff.
It depends also on the layers also, but yeah, die by die is more popular.
Thanks.
Yeah.
Gopal, one quick question. Where is the
Sure.
silicon? In the previous slide, where is the silicon here? You said metal is being etched.
Murli,
Okay.
Murli, please, if anybody has questions, please put them in the chat box, and Vas will see whether it is appropriate to halt the talk and to pose the question.
Thank you.
Otherwise, all at the end. Please, thank you.
Let me answer this question. So silicon, you start with silicon, Murli, right? And then what you do is build the transistor. After building the transistor, I put an insulating layer on top. Now I have 2 transistors that I need to connect. So then I put a metal layer. And by the way, there may not be one metal layer. If you think of it, it may be hard to connect in one layer. So what you do is you do one layer, then you put insulator again, put a second layer. Let me show this picture. So what happens is you get your wafer first. You saw it out of an pure crystalline silicon, you polish it. Then this loop goes over and over. You deposit metal. You deposit metal, you deposit photoresist, you expose the photoresist, you develop the photoresist, and then you perform your etching or whatever you want to do, and you remove the photoresist. And then you go back, deposit the next layer. So you keep on going through this loop. And in modern technologies, you can have this layer, this loop, about 40 to 100 times. Not to say you have 100 layers, but the same layer may require 2 or 3 loops around this. And finally, when you have your whole stack, you come out and your wafer is done. And then you cut it and all that. Okay? So this is how it looks. So if you look at this picture below, this is an Apple M1 die. And this is a cross-section, vertical cross-section. So if you look at it, you really can't make out very well. Your transistors are sitting at the bottom, down there. Okay? So what you are doing is each one of these is a layer of metal. Okay? So you can see metal, 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 metal. So for each one of these, you might have had 2 or 3 rounds of depositing photoresist, etching, depositing photoresist, etching, and so on, and so on, and so on, till you come to the top. And at the top, now you can connect. So on the right-hand side, this picture sort of, this is an IBM picture actually. So somebody etched away all the insulators to show you how each of the metal layers stack up. Your transistor is way at the bottom, but, and you can see this is like a skyscraper, right? Your transistors are tiny, but this stuff is huge. And the other thing I forgot to tell you guys is the critical dimension is this length from this end to that end. This dimension is the critical length. So when somebody says it's a 2 nanometer process or a 5 nanometer process, this distance is the one which is 2 nanometer or 5 nanometer. As you go up the chain in metal and stuff, this is no longer 2 nanometer. These are things, metal, and the reason is very simple. If you make a metal line which is 2 nanometer wide, the resistance will be just huge. So nobody wants to do that. So these are much larger. So when somebody says 2 nanometer, they're only referring to the bottom transistor. Everything else is much, much larger. And you can see here, as you go higher and higher, the dimensions become larger and larger. And another reason is it's hard to, for all you photography fans, if you don't have a completely flat surface, it's hard to get focus. There's a depth of focus. So as you go higher and higher, you don't get a flat surface. So you cannot even do 2 nanometer here if you want to, because your depth of focus for 2 nanometer is really tiny. Okay, so the good news is I think we are done with the fundas. So Vas, if there are any questions, we can answer here. Before
Let's take
the
a
rest
look.
of it is fun. It's much easier.
No, I think we're good so far. Keep going.
Gopal,
Scale.
just one quick thing, Bharat here. Could you
Yeah.
just explain what is this on the top of the transistors again? I know you explained it, but I didn't get it. What is the top of
Okay,
the?
so it's the actual wiring. So your transistors are switches, right? So now you need to connect, say, 1,000,000 of these switches. Okay, and you connect them using wires.
Okay.
So these are wires. Each one of them is a wire. And the reason why you have so many layers or so many types of wires is, if you think of it, right? I have a horizontal surface and I have 1,000,000 of these very close to each other. So I have to run wires from all over the place, and I cannot do it on one layer. So for example, if you think of, I draw verticals on one layer and horizontals on another, right? So I cannot intersect. So I need many, many layers to do the wiring. So that's what each of these is, a layer which connects your transistors or switches.
Thank you.
Plus, also some of them have to provide power to your transistor. So these big guys usually on the top provide current and power. Okay, now we get to the more fun parts of the talk. So first is scaling. Scaling refers to the process of reducing transistor dimensions. So if you remember the picture, the transistor looks like this. There's some N and there's some P. And this is your gate on top, which turns on, which is a capacitor. So as we said, this L is the critical dimension. And scaling refers to reducing this L. And we reduce the width also, but to first order, we reduce L. And why do we reduce L? So what used to happen was speed used to get faster for two reasons. Electrons take less time to travel this distance from here to here. And number two, your capacitance lowered because your L became small and your W became smaller. So LW is proportional to the area of the capacitor. So the capacitor went down, so your speed went up. So smaller capacitance, faster switching time for the transistor, speed goes up. But it's no longer true. So I crossed it out, okay? So this used to be a big driver for scaling. Number two, as you reduce this, you can lower voltage because the distance is less, so you can lower voltage. But again, voltage lowering died about 15 years back or 10 years back. So that again, and lowering voltage is also good. So if you look at power, it depends on how many times you switch the capacitance, what voltage do you switch, and what's the value of capacitance. So if you lower your capacitance and lower your voltage, that lowers your power. You don't want to lower your frequency because then you're going slower, so that doesn't help. So you want to keep your frequency high, but lower your capacitance and voltage. But again, the lower voltage stopped about 10 years back. Lower capacitance still works, so that does result in lower power. So the main reason for scaling now is you get a lot more transistors, right? Smaller transistors, you can pack a lot more. So that lowers the cost and helps performance because you can put a lot more stuff in there. So once upon a time, it was speed and power. It's no longer. So every one of you has heard about Moore's law. And I just wanted to show this slide because it's very interesting. Gordon Moore was one of the founders of Intel in 1967, did this little bit of work. So he took all these ICs at that time, and he saw which year they came out in. So you can see he's counted the number. This is from his handwriting and his documents, right? So he goes over one transistor. Then in 1962, there were 3 transistors, 4 resistors. So he counted till 1967. By this time, there were 264 transistors, and he calculated and he made this statement: number of transistors on a chip doubles every 2 years, right? This was called Moore's law. And again, the beauty of it is, by the way, it's a law for, I don't know why it's called a law, but it happens. So he made this prediction on 200 transistors. Now, over the years, when you look at it over 50 years almost, look at the number of transistors. Now, this is in thousands. So this is 10 to the power 7. This is 10 billion transistors here. So he made a prediction based on 200 transistors, and over the years, it's gone steadily, followed that law up to 10 billion. So this is a pretty amazing outcome, which I don't think he anticipated. And most of you have heard of Moore's law, but what was interesting to me was the fact that this prediction was made on 200 devices, and it extended all the way here, right? Some of the other things I wanted to show you was, so what was happening was initially, if you look at 1970 to 1990, the voltages were dropping, capacitances were dropping, frequency here, which is green, was going up, but the power remained in control, right? The power remained pretty flat. This is this orange curve. But somewhere around 1985, the voltage scaling started dropping. You could not drop the voltage as much. So the frequency kept going up because the capacitance dropped, but the voltage did not drop, so power started increasing. And so somewhere here were the first predictions that Moore's law was dead, okay? Because nobody knew how to increase power, control power. So this sort of struggle went on for a few years. So predictions were made saying by 2000, 2005, Moore's law would die. And then what happened, number two, the frequency stopped scaling. And the reason was there are two pieces to speed. One is your wiring capacitance, one is your actual device capacitance. So device capacitance started to shrink to a point where wiring capacitance became as significant as device capacitance. And so you got into a problem where your frequency stopped scaling. So your frequency does not scale, your voltage does not scale. What do you do now? So this was another time when Moore's law was predicted to die. But this is where, again, circuit design came to architecture, I should say. Circuit architecture came to the front. And so what people started doing was started putting more cores or more processors on the chip. So instead of having a single processor, you can see till now we only had a single processor. So instead of having a single processor, which was running faster and faster and faster to do more work, they said, why don't we put many processors all running at the same speed? But the advantage being each processor does a different piece of work. So I don't need to have all of them running at the same time. And since I don't have all of them running at the same time, my power doesn't explode. So the power sort of started staying in control. Performance started going up. And again, since you have more processors, you have more transistors. So interestingly, while Moore's law is true, there have been fundamental changes in architecture and stuff to keep Moore's law going. So while people say Moore's law, your Moore's law of today is not what Moore thought of when he came up with the law, but it still continues to grow. So transistors are continuing to grow, and there have been many predictions that Moore's law was dead, but it keeps continuing because of changes in architecture, a lot more because of changes in architecture than changes in process. So originally it was a process-based rule. That process develops over time. It's changed to an architecture-based rule now. And so where are we going with this, right? So first of all, remember I showed you this picture where the transistor was flat and under the surface of silicon. The problem that happened is as you bring these two closer and closer, you start current leaking from here to here. And when current starts leaking, because this is getting really close, then what happens is your switch is pretty poor, right? I mean, you want a switch which is off or on. Now, in the off state, you're letting some current go. So this did not work. So now what they did about 7 or 8 years back, they started going three-dimensional transistors. So instead of having this two ends, here are your two ends, which are called source and drain. And your gate, which was here, is now sitting across it, and it's covering three sides. Here it only had from the top control. Now it controls from this side, that side, and the top. So this is a much tighter way to shut off this gate. So this is called a FinFET, and these are called fins. So the transistor moved into the third dimension. And as we go forward, there are many, many variants of the same idea. And you can see it's a fully three-dimensional structure from being a 2D structure. All kinds of weird shapes and, things are happening. I won't go into that. There are good reasons for all of this. But today we are still a FinFET. We are going to go into something called sheets instead of fins. On the memory side, they had the same problem because you want to put a lot more memory into the same area, right? You want to reduce the size of each bit. And remember, the key is the capacitor, which stores the charge. So you need a certain amount of area to store charge. And how do you reduce capacitor area horizontally? So that's why they go into the third dimension. They make capacitors vertically so that if you look at it from the top, the area is pretty small, but vertically you have the same area. So going to 3D saves a lot of area for this. And remember, your wafers, you want to reduce the size of your die so that you can pack more die per wafer, because the wafer cost is roughly constant. So the more die you pack, you don't pay more for packing more die on a wafer. So the more die you pack, the cheaper it is. So the third dimension is getting to be really important for the device. We always had 3 dimensions for wiring, but for the device itself, both of them are moving into third dimension. So this is what you expect to see in the next 10 years is more of this. So if you look at a picture of a modern CPU, based on what all you've learned so far, and this is an Apple M1 Pro, which is used in I believe, in their latest PCs. So what you see, remember what we said, you'll have multi-cores. So you see they have like 8 cores here, 1, 2, 3, 4, 5, 6, 7, 8. These are all CPUs. And the benefit of this is you can assign different tasks to different CPUs. And I'll give you a very crude example. So for example, one CPU could be monitoring your keyboard, one CPU could be monitoring the internet and seeing whether you're getting any data and so on, right? So they don't need to be active all the time. So when you are typing something, that could be one CPU, there's another CPU which is doing something else. So that's why they have 8 cores. And plus they have 2 efficiency cores. These are low performing cores which are used when you're doing nothing. So they just sit there monitoring very, very low power. Then when you start doing something, they wake up these big cores. And like I said, there's cache. So there's 2 caches here, and then there's 2 more caches here, system level cache. And for graphics, they have 16 graphics cores for different functions. And this is the memory interface. So this chip is the CPU, which then connects to your external memory. Now, this external memory runs at about 1/100 the CPU speed, like I said. And you could have multiple chips here, depending on what PC you bought. If you bought 8 gig, it may have 2 or 3 chips. If you bought 16 gig, it may have 4 chips and so on. Typically, laptops that top out at, say, 4 chips, right? So this is your modern CPU. And so now
Just
if you look at...
interrupt, Gopal. So we are at 20 past the hour. There are a bunch of questions that have to do with the business context of all this and where business trends are going.
Yes. So we are going to talk about business next.
Yeah. So just keep in mind that that's...
Yeah. So skip all the business questions. If there are any questions related to this, so far to the process and the device, I think we should answer those.
Vas, there is no time limit on this talk. Gopal can go on as long as he wishes to.
Fantastic.
I'll try to wrap it up in 1 hour. I think we are doing good. I was thinking 20 minutes here, but all business. So I said, this is all the basic fundas. Once you got some feel for this, we can talk business and all that. Okay. So one of the interesting things is as you reduce the scale nodes, and you can see these are very complicated chips. You have CPUs, you have GPUs, we have This is a neural processing unit, plus you see all this other stuff sitting there. So what happens is your cost of designing these chips also goes up enormously. So previously, while it would take 20-30 million to design it, these latest chips, what like Shiv and all are working on, costs about 500 million to just design the chip. Okay, so the design costs are shooting up. So you can imagine what are these used for? So the scaled ones, which are, as you go tiny, are used for your smartphones, used for CPUs where performance is really important. That's where these guys go. On the other hand, the power chips are not scaled. They are like 100 times. I may have they're about 100 times larger in their dimensions. They're in the micron level, while this is there. So like automobiles and all live somewhere in the 90 nanometers. So not everything needs the scaled performance, right? It's only the high-end smartphones, CPUs that need these type of performance. Right? Recently, Huawei announced that they were able to make a 5 nanometer application processor for a smartphone. So that's where they are at for these kind of things. So when the Biden administration tries to ban stuff for China, they're worried about high-end CPUs, high-end GPUs used for AI. So they're trying to control them at this top level. We'll come back to the China story separately. Okay, so topic one, which is business models, right? What are the business models in the silicon industry? So first, in the 70s and 80s, semiconductor companies own their fabrication plants, right? A fabrication plant would cost 10 million to build, and they used to design and build. So Intel used to design their processor and build it in their own fabrication plant. And there's this famous statement by Jerry Sanders, who was the founder of AMD, saying real men have fabs. I mean, so this is a very famous statement, and this is the way industry was. Till about 1984, the first fabless startup was, and I put Dato and Gordon Chang started this company. I put Dato's name because he was an investor in my first company. So he's a great guy, by the way. So you can imagine foundries were costing 10 million to build. Dato used foundries of some Japanese foundries, which had extra capacity. And he spent 3 million and took his company IPO. Okay. So this was a real revolution in terms of companies which don't own fabs. They just say, we do design and we'll get it fabricated. We don't invest in fabs. We don't do anything. So if you invest in fabs, you need about 10 million to start off with, right? So this would never have happened. And then in about 1987, TSMC was founded by Morris Chang. And TSMC was nothing but a pure play foundry, right? And this is a big step from going from a company which designs and uses its own factory, let's say, to going to an environment where there are designers who do only design, and there are factory people who build only factories. So when TSMC was founded, they were two nodes or two dimensions behind Intel. So if Intel was X, these guys were like at 4X in critical dimensions. So this is how it started. But today, it is the norm. And the reason is there are two drivers. First is startup capital efficiency. So like I said, if you are going to build a fab, it costs a lot of money and it requires a lot of people. So it's not very efficient for one company to own its fab. And to give you practical examples of it, here are a bunch of the top semiconductor companies today. And this is a rule of 40, but without getting into that, all I'll say is higher numbers are good. Higher numbers show that you're using your capital very efficiently. And you can see all the top companies which do very well on these metrics are all fabless. So all the orange stars are fabless. So Qualcomm, Marvell, Avago, Broadcom, NVIDIA, AMD, all are fabless. If you look at the fab companies, Intel, really bad right now. Micron, not so good, right? TSMC, which is a pure fabrication company, does very well. So that's one of the primary reasons for a fabless is you use your capital better. Each group uses their capital for what they want to do. Number two is foundry economics. So what happens is in every generation, the investment to build a factory or a foundry is enormously high. So the latest 5 nanometer is not even the latest. This is a few years back. 5 nanometer takes about 15 or 16 billion to build this fab. And the problem is you built this fab with 16 billion. It takes you about 7 years to depreciate the cost of building this fab. But then Moore's law says you want a new process node every 2 years. So the question is, you built this fab, and let's say I own the fab. What do I do with this fab when I do the next generation of chips? Because I need the next generation. I want to go to 3 nanometer to be competitive from a chip performance point of view. But my fab equipment, I've spent 15 billion and I'm not using it. It takes me 7 years to use it all up. So this is a big problem when you own your fab. And so one of the things when you look at it, foundry economics, so let's say you're Intel. So in that quarter, you made 12 billion, okay? So you own your foundry. So of this 12 billion, you have to spend a lot of money on your own foundry. But then you look at the fabless people. So Apple Apple buys about spends about $16 billion on a foundry. Similarly, if you look at all the fabless, right, like NVIDIA, Broadcom, Qualcomm. So all these fabless guys are spending 58 billion in that quarter. Intel spends 12. So now if you are a factory that has access to business from all these folks, you get a business worth 58 billion, while Intel gets business worth 12 billion because it's only their own. So these guys who are fabless get access to a lot more revenue than Intel or TI, for example, do. So if you look at it, so what happens is this is the critical channel length over the years. So if you look at it, Intel was much better, lower is better. So Intel was doing very well, and TSMC used to be behind Intel. But over the years, all this investment went into TSMC. And then guess what happened in about 2015? TSMC overtook Intel. They started making smaller features and spending their 15 billion on a fab. Intel got into trouble, and Intel could not scale as fast. So this again shows how the economics of foundry, having a pure play factory, which takes circuits from a lot of people, works much better than having your own foundry. Now, Intel also is trying to get into the foundry business.
Exactly. And why would it not? I mean, it does its own chips and it gets others as well. It does
many reasons. First of all, the Intel foundry is not very efficient. Intel CPUs, their yield is very poor. But Intel was selling CPUs at $500 and $1,000. So they didn't particularly care if it cost them $100 to make the chip. Okay. On the other hand, most of these other companies, the chips they sell, Qualcomm and all, they're like $3, $4 chips. So you need to have very high efficiency. That's one problem. Number two problem is Intel was very secretive. At one point, they thought they had the best process. So they were leveraging process benefit in addition to their circuit design so they used it as a differentiator. So they didn't want to share it. Now it's no longer a differentiator. In fact, they're worse than TSMC. And then there's a third, more technical reason in terms of IP. What IPs do you have in your foundry? So when Apple goes to TSMC, and Pons mentioned this in terms of layered software design. Hardware design is also layered. You don't build, if it's a 50 billion or 5 billion transistor design, you don't design it in terms of transistors. Design it in terms of circuit blocks. So for example, you buy a CPU from ARM and put it in there. So things like that. So then there's a question of, do you have IP in your foundry? Because if you're missing IP, this is a big problem with Intel. It's hard for me to go design there because you don't have all the blocks I need. And I don't want to be developing these blocks, right? So those are some of the reasons why. But Intel is trying. And by the way, this is the third time Intel has tried. I've been part of the first one in 1987, and it failed. They tried again in 2000. And it's also a mentality. They don't have a service mentality. TSMC has a service mentality. And that's not to be discounted. I mean, that I think is one of the biggest issues. If you don't have a service mentality as a foundry, it's a problem. Intel cannot make up its mind. So this is the other interesting slide. So if you look at foundry capacity by country, so now you guys understand what's logic, what's memory, and these are other stuff, discrete and analogs. So if you look at percentage of global chip production, right, 33% goes to memory, 2% is less than 10, 10 to 22 is 8%, 28 to 45 is 9%, and greater than 45 is 22%, and discrete analog is 26%. So you can see when you go to this really advanced nodes, it's all Taiwan, which is all TSMC, and then there is South Korea, okay, which is Samsung, basically. And if you look at China and stuff, you see that their fabs, they dominate the larger dimensions, right? They're not in the scale. So now we've heard a lot of stories about India wants fabs. So the question is, what do you want to build? So if you go 10 nanometer and stuff, it costs you about 15-20 billion to build it. And it covers 2% of the global chip production. You go here, it covers 22, much cheaper to build, but you have plenty of competition. Everybody has it, right? So this is a very interesting story. As people say, I want to build a fab. It's a bit more tricky than that. We'll come to other issues with the fab. But what do you want to build and why? And do you have a play? Is an interesting question, right? So this slide sort of shows you what the status is. So that was all about fabless versus fab and stuff. Any questions on that? We can address any questions, Vas.
So there are a couple of things. One, it would really, people are interested in your personal story, involvement in all of these things, where you have some interesting anecdotes perhaps about that. That's one. And the other thing is about from Bharat and Shirish and I think Arul. You can read the stuff there. It's all about the US CHIPS Act, China, where's the competition? Are we going to catch up? And you already brought up the India point.
Okay, so there's a full China section I have. So we'll address that in the China section.
Okay.
And my story, I'll come back to it at the end of it if we have time.
You said we have time. So you're not going to risk it.
That's why I think I want to cover this and then we can go off into these other topics and spend as much time as we want. GPUs. This is more on system architecture. And let's look at what the story is with GPUs. So remember, we're talking of CPUs. They have a couple of cores and this whole memory story. The GPU story is completely different. So the blue represents your cores. So what the GPU does is it says, I'll build a CPU which has very limited functions, right? It can, let's say it can do multiplications, it can do additions, and it can do some very little logic. So a typical CPU may have, let's say, 400 or 500 instructions. These CPUs have maybe 50, 1/10. So they're really, really small CPUs. And what you do is you put some memory next to the CPU. Then you put all the CPUs, they put some more memory next to this group of CPUs. And then eventually you go to external memory, right? So I just said memory speed, this one, if it's 1, you get closer, it's 10 times faster. And the ones which are right next to it are 100 times faster. So while a typical, like we saw the Apple core had 8 CPUs, a GPU could have many thousands of cores. So what this allows you to do is if you have an image, there are applications which happily can be split into many, many pieces. Like if you're processing an image, I can process, let's say 100 pixels separately from the next 100. I don't have to, there's no relationship between this pixel and a pixel which is set at the other end of the image. So what this allows me to do is to take a picture, which I have in memory, then I cut it up into pieces, feed it to each of these processors. Each of them does a little bit, pushes the data back into memory, and boom, you're done. So this is a problem which is easily parallelizable. So if you can parallelize the problem and you have thousands of CPUs which can act on it, hey, you've solved the problem much faster. And again, remember, these processors are, why can't Intel do the same thing in their processor? Because their processors are large and they have thousands of instructions. They have to be backward compatible. So they cannot drop instructions. And plus also you need instructions. You need a lot of instructions for normal programs. So these are not normal programs. So for example, I cannot replace a CPU with a GPU, okay? Because you can't run all code on GPU. It does limited functions, but it does them fast and efficient. So that's the idea behind that. So graphics, normal. Now, when you go to AI, it's not like NVIDIA did this, but it happened. So for example, matrix multiplications is a big thing in AI. So what is a matrix multiplication? If this goes, if you're not familiar with it, that's fine. But the whole idea is you take a row and you take a column, you multiply each number in the row by each number in the column and sum it up to get one output here. So A times B, so that way each row, each column gives you one output. So what do you do in a GPU? What you do is, so I have this big matrix here, big matrix here, and big matrix here. I take this A0, B0, 0, I bring it into one of the processors. I do the multiplication. I store it in a local file. Then I bring A01, B01, bring it here, multiply. And now I already have one piece. I add to this piece, and then I take it out. Now, don't worry if you didn't understand it, but the basic idea is you take a matrix, chop it up, and give each piece to one of the processors you have. And since you have so many processors, I take a big matrix, give each one a little piece. I can do this very fast. And so what has happened, and so how does this kind of a chip look? It looks like this. It's got a lot of processors, okay? And these are two caches right in between. And so each one of them can run very fast. And this has 80 billion transistors, this chip, right? This is in TSMC 4N, which is something like a 5 nanometer chip. But so while we can do this much processing, right? So we improved our processing skills, everything. But still what's happening is, in terms of models, AI models, in the last 2 years, the size of the model in terms of parameters has gone up by 410x. And here are various models, including GPT-3. So you can see how these models are crazy. Guys like Vas keep on getting new AI models and they keep increasing. Our memory on this GPU, this is the external memory. This is the big memory that you have here, right? Is only increasing, by a factor of 2. So there's a huge gap between the size of these models and how much one chip can handle. So guess what? When you have to train something like GPT-4, you need 15,000 of these GPUs. And remember, each GPU is so much faster than a CPU. So you can imagine if you're doing this on CPUs, you would never get anything done. Even on 15,000 GPUs, it takes about 4 to 7 months to train it, because you have to do about 2e to the power 25 number of ops. I don't know if it's 2e, it could be 10e to the power 25. That's a substantial difference. I think it's 2e to the power 25 ops to train. Okay, so that is the kind of stuff. So
Zoom.
guess what? If you're buying 15,000 GPUs,
Or a XCMC what presentations.
no, if you're buying 15,000 GPUs, guess which company is doing well. So here is NVIDIA stock over the years, and you can see somewhere around here is when GPT-3 was announced, and you can see what happened to the stock. They cannot produce enough chips today, right, to cater to this market. And the fact that even GPUs are not the most efficient way to solve this problem, but still they keep going. So this is the story of GPUs. So the point here is, given a certain problem, stuff that we were doing in software gets much more efficient when you move it to hardware, but you lose flexibility, right? You can't do stuff. So this is a kind of a process that happens over the years. Stuff is done first in software, and once there's enough demand, you move it into hardware. And then that custom hardware increases the efficiency. Anything on GPUs, Vas? Any questions on that?
No, I mean, I would say it's a little bit different. The whole point about scaling at the software level with the large models, that's coming about fundamentally because of scaling of the parameter space. So the whole programming model completely changed. And in that sense, I would not even consider it comparable to what happened 20 years ago when you're looking at single-threaded, von Neumann machines and trying to parallelize them extensively. Yes, you are right that NVIDIA kind of lucked into it, but
yes,
they kind of knew that the matrix multiply is going to be a big deal. They didn't know exactly how, and they built a whole company around it. So, maybe they deserve their luck.
Yeah, I mean, there's definitely a lot of luck. But anyway, so that's GPU versus CPU. Next topic I wanted to cover, which is of great interest, is China. What is China doing? What are we doing? How does it line up? So if you look at it, semiconductors are China's biggest imports, more than oil. At least this was true 2 years back, right? So semiconductors, they do 233 billion import, and oil is 185. So that shows you, and they think about these things quite a bit. So this was a problem. So what they did was, starting in about 2000 onwards, they put a lot of money into manufacturing grant subsidy, federal taxes, federal incentives, and so on, right? And you can look at this table, and the US over the same time had zero. Recently in CHIPS Act, US came up with 39 billion. They gave 25% tax credit, and they put another 10 billion in the ecosystem. So they're fighting hard. But the Chinese story was very interesting. In 2018, 5% of internal chip demand was produced in China. Today, 30% of internal chip demand is produced in China. So all the money they spent and all the planning they did has helped them substantially. And I want to show you, it's not just building foundries. They thought about the whole ecosystem that we spoke about in the beginning. So they have invested in things like wafer fab equipment. They have invested in chip design companies. They have invested in IDMs, or integrated device manufacturers, which are memory and logic companies. And they invested in foundries. So they have invested across the whole ecosystem, and not just say, I'm going to build a foundry. And this is really important, because building a foundry requires a lot of support. I mean, if you can't buy equipment, how can you build a foundry, right? And this is not my statement, I copied this slide, but massive IP theft from Taiwan and US semi industry is true to some extent, right? So that's what China did. And to give some more details, they have been developing fabs like totally across. So in terms of how many wafers per month they can produce, you can see in 2019, they're producing about 600K wafers per month. They have quadrupled it They produce 2,200,000. That's 2 million wafers a month, right? In the future, they will, sorry. So they've invested in all these foundries. And this sort of shows you how much of that is scaled and how much of that is not, and stuff like that. And in terms of equipment, don't worry too much about the names, but the bottom line is green these are various steps in your process which require different types of equipment. The pink ones are the ones China has. These are all Chinese companies. So you can see in every phase, they have their own companies building equipment in addition to buying equipment from outside. So this is not a one thing like, oh, I'll just build a fab. They build equipment for the fab, they build design for the fab. So they are really doing this a full ecosystem play. So one of the biggest barriers, and which is where Biden and company are trying to slow them down, is lithography. Remember, we spoke about how do you draw patterns on this stuff. So if you look at this, as you go down the chain, there's only one company today that has lithography at 5 nanometer or below, and that's ASML. So they're trying to block ASML from sending stuff to China. But then there was this recent thing saying, hey, Huawei announced that they did a 5 nanometer design, right? Or 7 nanometer, I forget the exact number. So how did they do it if this was all blocked? And the answer is, if you have a 10 nanometer capability, what you do is you first print 10 nanometer features, then you move the wafer by, let's say, 5. You don't move the wafer. You keep the wafer the same. Then you take a second mask, which is offset from the first mask in the middle, right? So now you go through a second phase and use a second mask and print the other 5 nanometer stuff. So overall, you get each one of these masks is 10 nanometer spacing. But when you put them both together, you get 5 nanometer spacing. And now you can process it and etch it, and you can get 5 nanometer features. The problem is, of course, this is very slow because you have to do it like 2 or 3 times. And it's got low yield. But it can get you to 5 nanometers. So the belief is the Huawei 7 nanometer chip at SMIC was done using some kind of double patterning. And getting below 5 is very hard. You can get to about 5 using these tricks, but it's expensive, it's not efficient. But the story is they don't care because SMIC, which is one of the biggest foundries in China, has not made a profit. It's fully funded by the government and they run at a loss, but they don't care at this point, right? So that, and by the way, this ASML, I just wanted to show you this. Oops, sorry. This ASML 5 nanometer thing. Remember, I showed you a very simple picture of you take a mask, shine light through it. That's not the way it's really done. This is how you really do for like 5 nanometer lithography. You start with a plasma source where 50,000 drops of tin are fired onto a vacuum chamber, and then you hit it with 2 laser pulses, and then you ignite the tin plasma, which is at about 220,000 degrees C, and that emits the radiation, and then you can see it's got really bizarre optics to get it drawn on the wafer. But fundamentally, the principle is still the same. But this is the equipment that they're trying to withhold from China, right? So the China summary is there are Chinese competitors in every stage of the semi-value chain: chemicals, materials, tools, and manufacturing. There's a tidal wave of government and venture capital and engineering talent. SMIC and Huahong, which are China's 2 big foundries, spent more on capex than they generate in revenues. If you think of it, that's not a model that's sustainable by any Western company. And in markets with forget that, and China's actively diversifying the semiconductor supply chains to domestic sources. And one of the things is the West actually turns out to be a key enabler. While the governments are trying to stop it, companies are not motivated to stop it because the manufacturers, China buys a lot of manufacturing equipment. So people want to sell to China because that's a big source of profit. So they fight export control and they send equipment to China. Other big piece of it is EDA companies. So for example, I told you how you can pattern using 2 masks. And all this is done in the EDA level, right? You just draw it and the EDA tools will split it depending on how you want to do it into 2 masks or more than 2 masks to do that. But there's no restriction on EDA companies. And EDA is one area where China is really weak, but they are jumping on it, and EDA companies are still doing joint ventures and training new Chinese engineers. So, and this is not restricted. And so that's another way they are catching up. They don't want to let go of that. So that's sort of the picture of China and what they are doing, right? So any questions on that?
There are actually a few other piled up questions, so maybe just take a few minutes and go through them.
Yeah.
So from Murli, what are typical quality defects in chip foundry manufacturing? He mentions EOS, foreign material contamination, etc. So what's the quality story there?
The quality story, first of all, it starts with the silicon wafer itself. You need very, very high quality silicon. Number two, the other sources of defect are all related to your foundry in terms of every step has a different type of defect associated with it, like photolithography. If what happens is when you put acid, like I said, you open up a hole, pour acid, let's say. When you pour acid, the acid is also eating your photolitho layer. And if it eats up enough of the layer, then it's a problem. Your hole becomes wider. Similarly, when you have 2 metal lines going next to each other, and you didn't get rid of all the photo, then what happens is there are thin whiskers between the metal lines which act as shots. So like that, there are many, many defects. So there's no one defect. But typically you want yields, the yield is directly related to the cost. So the higher yield, the lower the cost. And people like Apple and all have very strict requirements of TSMC, right? When you go to a foundry, the foundry says, if you follow all my rules, I will guarantee you a yield of, say, 95%. So if they can't get 95%, they have to eat the money. So it's very important for foundries to have good yields. And TSMC, like we were talking, TSMC has very good yield compared to Intel.
Thank you.
So that's yeah.
So there's more coming from Murli. ASML is dependent on a small group of exceptional mechatronic designers and IP. They live in southern Netherlands. And it's just a comment, I guess. Many employees IP are from Philips. Sanjay has a question. What are D0 levels? I don't know what that is at a modern TSMC fab.
Oh, that's a good question, but I don't know the exact number, Sanjay.
Yeah, but 95% is a fair enough number that, whatever the D0 levels are. If they're
that D0 is a technical number.
Yeah,
and I don't even know whether they let it out.
95% is good enough.
Yeah.
The other question that Vas ignored, which was on an earlier section, was so memory bandwidth. I mean, all these companies like, again, I'm dating myself, but Rambus and stuff had developed technology to improve the memory bandwidth. Are they still relevant? And which layer of memory do they play in still? Are they at the cache level, or are they still external memory to the CPUs, etc.?
They had IP. And so this was a big story. It's a very interesting story. So what happened was there's a Rambus worked with Intel, and there was one generation of Intel processors which came out using Rambus memory. And Rambus was an IP player, so they wanted to charge all the memory manufacturers. to use their IP. And the memory manufacturers hated that. And so what happened was they formed an association called JEDEC, and they started developing standards for memory. In memory, the biggest thing is cost. So these guys are very, very, very cost driven. And so they came out with their standard, which was, you can argue about it, and Rambus sued all of them. So there was a big battle, and so they finally settled over the decades, and it's a decades-long battle. So what happened was eventually the Rambus approach was not chosen for bandwidth. They went back because it was more expensive, and Intel also dropped them. So it was basically came down to cost. And so what they landed up doing was just using very simple interconnect technology and essentially making it broader and broader. The interconnect, instead of having, say, 32 bits, now they run at 128 or even 256 bit wide. So they can run it at a lower frequency, but send as much data. So that's sort of roughly what happened in that story. So Rambus does not make memory.
In research, people used to always talk about, in the end, needing optics there. Is there anywhere close to the horizon to becoming a reality, or are we still a decade?
There are at least 10 companies, startups, especially for AI, because remember I showed you how much memory you need. So for AI, there are at least 10 companies I know who have some form of optics and trying to use optics for memory. So very active, but nobody has shown anything good. In fact, Intel, which has been investing in optics for a long time, recently announced that it was going to can that division. So, it doesn't mean anything one way or the other, but after all this investment, Intel is dropping precisely that memory interface story with optics. But there are at least 10 startups I know who are vigorously pursuing the optical story.
Thanks.
So there was a question from Rohit Vishnoi, which I didn't completely understand. Rohit, you may want to repeat it, but it's essentially about what are inefficiencies as you're abstracting layer by layer. And what I don't get is which layers are you talking about, maybe in this stack.
So it's a very general question, Vijay. So both in software and in hardware, right? The only way to make this huge complexity work is to abstract at each layer to make it easier to actually execute, right? So what is the inefficiency as you abstract?
Inefficiency.
Is there any measure of that? Do they, probably nobody cares, but I'm just curious.
Yeah, there is a abstraction. You're absolutely right, Rohit. Any abstraction, of course. So when I take a big block, let's say I use an ARM CPU, there are many features, many instructions there which I may not need, for my application. So if I'm Apple, I'm building this stuff and I own the OS also, the operating system. There are many instructions in there I don't need. So I could go in, if I was building my own CPU, I could go in and remove all that, but then it would take me a couple of years to build my CPU and then get to work. Instead, buy it from ARM and move on, right? I've got the compiler, I've got everything that ARM provides. So yes, there is a lot of inefficiency, but again, 1 million transistors, who cares, right?
Exactly.
When I have a chip with 5 billion transistors.
But when you're coming up against limits such as in AI, does it matter? Or there is just the design problem is so complex that you don't care?
Fundamentally, you try to solve it with architectural changes, not changes in the block. So I may use, say, 20 ARM cores and figure out some architecture that's more efficient. But I would not go in and change the ARM core itself.
I see.
Right. So most of the interesting work in chip design architecture is how do you plop down these blocks and interconnect them in some kind of a clever way to extract performance. For example, there's a USB block. Nobody would go and do hardware for USB, for example, today. That would be suicidal. So you buy a USB block, put it in there, and now I just connect it to USB. But now that USB block may not be the most efficient because, for example, there are many USB modes. I may not want to support all of them, but guess what? Just throw it in there and move on.
Yeah.
Right. And if you look at it, I didn't get into this a lot, but in chip design, there are two things that are driving chip design costs. One of them is verification. How do you verify that the design you have is actually working?
Yeah.
Correct.
Before you ever send it to the foundry, I presume. Yeah.
Yeah, before you send it to the foundry. So the problem there is, if I'm going to do my own CPU, now I have to verify that the CPU works properly. Instead of that, I take an ARM CPU. Hey, it's guaranteed that it works. So I don't have to look inside it. I can verify at upper level. Number two problem is software. Software is over 50% of the costs associated with chips today, chip development. And again, do I want to, I build my own CPU, I have to build my own compiler, I have to build my, a whole bunch of shit that is
I
not.
get that, Gopal. I get that the challenge is prohibitive. I'm just curious as to what the efficiency loss is in all of this. Is it 10%, 50%?
No. It's probably 10 to 20%.
That's it. That's it.
Yeah, that's it. I mean, again, it depends on how clever you are in your architecture, right? It comes down to, because, for example, ARM processors, there's a range of ARM processors. And if you choose the right ARM processor for your task, you're better off. Now, if you choose an oversized ARM processor for your task, then of course you're being more inefficient. But that's where your architecture skill comes in, to choose what you require and choose the minimum amount you require. Don't have too much overhead.
Got it. Thank you.
Yeah,
I have some thoughts on this as well, Rohit, but I'll defer it to the end. So there are a couple more questions. Let me get to those. Sunil Gulati has, do you want to say that India has missed the chip bus already, or it can still get on board with government investment? Can private sectors do it alone?
Gopal, can you stop share screen so that now we can see each other?
Wait 1 minute. I have one more section.
More slides. He has more slides.
Yeah, we're not done yet. Okay, so why don't we do this, Vas? Let me finish that. I have only 3-4 slides more.
Go for it.
Let's finish that and then we'll come back. Okay, so future trends, there are not too many. Custom AI inference chips. This is what we were talking about. You don't need all these CPUs and all this kind of architecture. So for example, you could go with an architecture, this Google has this, where you have a lot of multiply units and all that, right? This chip looks very different from your normal CPU. So this can be much more efficient. And if you see below, this is from Google, so this is a bit perverted in terms of metrics. But you can see they claim that it's better than a GPU. So, some architectures like that. The other big thing where nobody's made much progress is kind of a funky phrase, non-von Neumann architectures. Remember, we spoke about an architecture where the CPU gets an instruction from memory, runs it, goes back, fetches the next instruction, runs it and stuff. Instead of that, this sort of looks like your brain. So you have neurons and you have synapses, you connect all these neurons and run stuff on it. So just to give you an example, Intel had this a few years back, and this type of an architecture, they came up with 128K neurons. And I just want to point out that a cockroach has 1 million neurons and humans have 20 billion neurons. So how do you program this is a nightmare. Okay. So but this is, people have been working on this. This is, if this is successful, and I almost believe this has to be successful for us to make the next leap in AI and in programming.
Okay, we're going to debate that. But
we can debate that. But
yeah, let's finish this.
Yeah. And then finally, chiplets. So Moore's law, this is one way to, again, extend Moore's law. So what you do is, instead of having one chip, you build many chips. The advantage is, so Rohit asked the question about efficiency. If I have USB, for example, USB runs at a very low speed. It doesn't need a 2 gigahertz or 4 gigahertz process. So what I can do is I can build blocks in various processes which are right for them. And by the way, I test all of these so that I know this is a working chip. And then I can slam them onto one silicon substrate and wire it all up and put it in one package. Now, do you call this one chip? I don't know. But fundamentally, you can build chiplets. And this is where AMD's already started this. And amongst other things, this is financially very nice because if somebody wants a larger cache, I can put a larger cache and charge them more. And somebody wants a smaller cache, I can put a smaller cache. So this is yet another thing that's coming along. And for further reading, I strongly recommend this book. It's called Chip War. It's a very nice book and very little. And with all the information I've given you today, you should be able to understand it even better. So I would recommend you read that. And finally, there is no thing without a quiz. So I have a quiz link here. And to tempt you guys, the person who gets the highest score, there may be many, so then we'll have to randomly draw. We'll get a copy. I'll send a copy of this book to them. And if you look at it, if you click on the quiz, I'll just show you. I can only fill it once. So you'll get a quiz like this. I don't want to show you the answers. So please try it out, okay? It's very simple. It'll take you 5 minutes to do the quiz. It's all click, and there's no
put the link in the chat, Gopal?
Yeah. I'll put the link in the chat, and I'll put the link on our WhatsApp groups also. So I'll give it a week. So please do the quiz, and we'll see what you learned, and it should be fun. It's nothing serious. So that's all.
Will you be publishing everybody's scores or just the winner?
No, I'm not publishing anybody's scores. I'll just let you know who the top
Come on, this is IIT, man. You gotta have everybody's scores.
I'll put out the statistics. Google allows me to collect.
I want to get a C or a D. I have a PCO, no?
Okay. Okay, switch off the share screen, please.
Yeah, now I'll shut off this shit. And by the way, there's also more material here after this. So,
yeah, great.
Okay,
Fantastic.
good. So, Gopal, I have a question.
Yeah.
Raghavan Rajan in a recent interview said that India should not be trying to go into chip manufacture at all because it is very capital intensive and gives very few people employment. And in any case, these chips go out they become obsolete very soon. Whereas India has about 20% of the world's chip designers. And given that it is the chip designers, NVIDIA and so on, that are trillion-dollar companies and some of the chip manufacturers are not, that perhaps that there is space for us in that area. What do you have? What would you say to that?
I think he does make a lot of sense. So a couple of things about the fabs. Setting up fabs is expensive at the high end nodes, right? But if you look at it, there's about 30-40% or more, 50% of chips are in lower end nodes, which are not that expensive to set up. Okay, so that's one thing. I'm not saying you should or you shouldn't. All I'm saying is it's not that expense depends on what fab you're setting up. And there's plenty of stuff to do at the lower end that you could play in, number one. Number two, fabs are a very dirty process. Okay, it's a very dirty business. You deal with dangerous gases. You provide the wastes coming out are really bad. And number three, which is a recent problem, it uses a lot of water, lots of water. So these are all things that you have to be careful about while setting up a fab, because if you're sloppy about safety, for example, some of the gases they use, you could easily cause another Bhopal, okay, much worse. So those are the things against the fabs. I'm in two minds whether you should set up a fab or not, okay? But on the other side, saying we could set up, we have a lot of engineers who are in design. But if you look at it and, being on this side and setting up India design centers and stuff, what people are doing mostly is they're sending low-end design. So the design is already done. Now you have to redo it. Those are the kind of jobs that are being sent to India. Okay, so while we have a lot of designers, they're designing most of the stuff is already designed. Okay, go move it from one process to other. I want to go from TSMC to some other foundry, right? So take this design which exists, redo it, rerun it, verify it, and ship it to another foundry, right? So so it's not very clear to me that you can just go in and start building billion-dollar companies there. There are investments and stuff. So it's all a mess. In general, there's not a clear-cut plan on I still don't know what we want to achieve, right? What do we want to achieve? I mean, building a fab is not an achievement.
Exactly.
Do you want to be independent of importing any silicon? Do you want to be, like for example, what Raghavan said about designing chips. What's the purpose of designing these chips? Right? So I think we need to have a more concrete, what do we want to achieve? We want to cut our chip import expenses. So it's not clear to me what we want. So if somebody can state that goal clearly, then all these are actually all these other decisions are easy to do. I don't think they're that hard.
But Gopal, if I could just jump in, let me turn this around. So what is remarkable to me is that China has gone down this path. They have figured out a certain strategy, as you are saying, a pretty holistic strategy across different layers of getting stuff done in this space. What was their goal? What was that story? It seems to me there must be an amazing story there about how they pulled it off. Sorry, just one more thing. I would say the heart of it, what this, not just this, but other such things are raising in my mind is I'm questioning the centrality of the corporation as the central unit of innovation in modern capitalistic society, particularly in the context of you're going to need governmental stuff. So what kind of governmental plus private entrepreneurship, what forms that can take? To me, that's the big question as we go into massive AI projects, massive build-out projects. So anyway.
Yeah, so I think China's thought process was very simple. They long back realized that semiconductors form a big portion of your economy, not just money-wise, but they're embedded in so many things. And one of their big fears has been lack of access to semiconductors. I mean, and the whole ecosystem, when I say semiconductors, the whole ecosystem, right? So for example, AI is critical. But today, magically, if China didn't have access to any AI chips, they would be dead. So that is, so they saw that. And the other difference between China and India, which may change, is China, the whole communist story, they have this fear of getting isolated, right? So that's one of the reasons why they saw long back that we could be in deep trouble if all these things are cut off. And then finally, it was a pure economic decision also. They build all these things and they have to import chips for building those. So when you're building it, and you can move the chips into your own country, that's a huge, huge win. So I think those were the things they thought of long back.
But then if they're not yet making money...
supply chips at a subsidized cost to these people who are using the chips in China, right? So, I mean, that's...
Yes.
Because if you import it, you're not getting those,
Yeah, so it's a full ecosystem play, right?
Yeah. And team, it's not limited to chips, right? I mean, I've sat across from Ministry of Health officials or whatever, they beat up on us for medical devices as well as IVs, as well as drugs, right? They want to be self-sufficient in everything.
Yes. So that's
possibly for the reason you mentioned, Gopal, of being cut off, right? So they
Yeah.
would, like, you would bring new technology to market, they would push you to manufacture it locally, and then they would topo it
Yes.
shamelessly within a year.
Yeah. Yeah. No doubt about that.
But
Sap,
then when
what
you
do
say, so when you say they want to be self-sufficient and so on, and they are subsidizing other sectors of the economy, but if they're not making a profit, in the end, they're digging a hole for themselves, and they're in pretty bad shit right now economically. So how
No,
long
but
is
they're
this
not.
sustainable?
Why are you saying they don't make a profit? Because what they're doing is they're building. So, for example, take a simple case, right, of the Apple iPhone, right? So they are building the Apple iPhone. Now it's, of course, fading, but they're building the Apple iPhone and selling it, right? So there are plenty of people working on it. And now they're buying chips from outside that go into it, right? Foxconn has to buy chips from outside. Now, if you're building those chips inside, more people work on building those chips, and those chips are cheaper, and the profit, it's more profitable for Foxconn to build using those chips than outside chips. So overall, economically, in time, it may not be initially, but in time, it will make sense.
No, I get it that in time they are hoping that it will make sense. But if you are subsidizing the chip user, and you are actually, and you are also subsidizing the chip manufacturer, then that subsidy has to come from the government. It is ultimately, it is a hole in the government's pocket.
Yes, but think of the other big danger they face is they can be cut off from rest of the world, as Rohit also said.
No,
right?
that I agree.
So
From security point of view, it makes sense. But economically,
yeah, so it's an
that is a question.
existential no. So there's an existential danger, and what do you do about that? Is you start investing and try to make it self-sustaining over time. The goal is to have self-sustaining.
Saurabh, your argument with is a good economic argument, but understand that every government at every level does it, from the governor who subsidizes a factory to be put in the state.
No, I agree.
Yeah, everybody does it, right? For employment in their local area. It does not make economic sense because you're robbing from somebody to provide employment, but everybody freaking does
Rohit,
it.
I agree.
Like if you're going to say you're Rivian and you're going to put together a new auto factory that's going to employ 3,000 people, states compete with each other to see who's going to give you the most.
No, Rohit, I agree with that. I'm only looking at the pure economics of for China.
Pure economics doesn't make any sense. Talk to me about football stadiums, man. 8 games
for
a year.
instance, you see, for even the agricultural subsidies given by the US economically don't make sense, but every government treats food security as a national security issue. So that the national security issue I get. I don't get the economics of it.
Yeah, but look at football stadiums. Why do cities give hundreds of millions of dollars for 8 games a year?
Let me try to bring it back to Gopal. One thing that came up, and I'm also very curious. Gopal, can you weave in your story into this, your startups? What were they about? How does that map into everything that you have told us?
Oh, man, my startups were quite boring, actually, because frankly, I mean, the startups we did. Okay, so let me see how to weave it in. So my startup, the first startup was, again, a fabless. It was a fabless startup. And when we started, it requires a bit of history, but we were working at Hughes Research Labs, and we were using a weird material called indium phosphide to do our circuit designs. And there were probably 2 foundries in the world which could do indium phosphide, and Hughes was one of them. So the thing about indium phosphide, it's super fast material. And at that time, optical communications was just going through the roof in 2000. And so, of course, we jumped on it with the indium phosphide, and the VCs were desperate to fund. So we had a stupid business plan, but we got funded. And so we started, and then like 1 year into it, we had the big internet crash and 9/11. So then the optical communication market just disappeared on us. And then this is where luck favored us. we managed to we got into the memory business. So not building memory, but there are chips that for servers, big servers, that go between the processor and memory. And so, and Intel, AMD and all control that. So we managed to have some really innovative circuit design, and we got into that market. So our end customers were people like Samsung, Micron, Hynix, and our further end customers were people like HP, people like Dell, and all those guys. So at one point, if you had opened any server, about 60% of the servers in the world were carrying our chips. This was Inphi. So we started as an indium phosphide company. We switched to silicon, and then we made a lot of money in silicon, and then we went to IPO based on our silicon revenue. And then it turned out that but we were also working on optical circuits. So no money at that time, maybe a few million. And that turned out in about 2015 or 2016, the stuff that we had designed in 2005 came in. And that really kicked the company up. So we were floating at about 100 million in revenue when we went IPO. But by about 2016, 2017, our revenue was running at about 600 to 700 million because of this kick. And now it was all these designs which were designed in 2005, which were being used now profitably. So one thing I learned, and then finally the company got sold to Marvell. After we were a public company, but Marvell bought it publicly for about 10 billion. And of course, I didn't keep my stocks all the way. If I had, it'd be a different story. But so that sort of was this. But the one thing I realized about startups based on that experience is a lot of startups build good things, but they don't have the time. They run out of money. If given 20 years of survival, a lot of startups that could be successful. So that's in short. And by the way, so after all this wisdom, when I started my second startup, I said, I know everything about this business, right? What's there not to know? And of course, I fell flat on my face. So starting startups is a good way to figure out your incompetence. You figure out your incompetence really fast.
I thought you said it was a boring story. Tell us about the second story too.
The second one was, it was actually technologically very, very intriguing because what we said was clearly, since voltage, like I explained to you, voltage is related to power. So to reduce power and do battery-based AI, we want to lower the voltage substantially. How can you lower the voltage? And it turns out, it gets more technical, but you can use, what happens is as you lower the voltage, there's wide variation in speed. And that's what happens basically.
This is ATA. This is your company.
Yeah, this is ATA. Yeah. So there's wide variation in speed. So if you have a clock which you want to run at a certain frequency, it becomes a big problem because the variation in speed is so large that if you want to spec a fixed number, that fixed number is very low, close to zero. So what we did was we removed the clock and we went asynchronous. And a lot of work, but it turned out that we were running full processors at even a quarter volt. Okay, so 0.25, it ran as low as 0.2. So at 0.2 volts, full processor running at a couple of 100 kilohertz. And it's quite amazing what you can do with that. So we did that. But then the problem was there is no market, for that application, which is AI at the edge, which is battery powered. AI today exists in the cloud. That's where most 90+% of the market exists. There's very little on the edge.
IP that could pay off 20 years down the road.
Yes, and we sold it off to these guys, MediaTek, which is a big Taiwanese company.
Yeah, but Gopal,
yeah.
lot of. I mean, I'm surprised at your view that not much AI. I think AI will be on devices a lot more than it is now, right?
Well, that's what we thought too 5 years back. And after that, I went to Microsoft. I was working on similar things. And we just cannot add up enough people. I'll tell you what the problem is. The problem is there are a couple of problems. One problem is most of these edge devices deal with the physical world.
Yeah.
Okay. And dealing with the physical world is a bitch. Because what happens is like things like, let's say you're counting people, okay, going through a passage. Okay, you put a camera there. And, now some guy comes along and says, oh man, this bulb is just taking too much power. Let me put a really dim bulb. Boom, suddenly your accuracy drops. And you don't even know that it happened, right? I mean, how do I know the accuracy dropped? Because all I'm doing is counting people. Suddenly I'm counting 0 people going through this passage. Hey, maybe that's possible, right? Nobody's going through this passage. So to overcome that, what you have to do is you have to build a full loop in the cloud. So every so often, you send raw data to the cloud, and then you study statistics of this raw data to see if something changed. And then if something changed, then you have to brighten the image, right? Okay, then you add some other steps to brighten, and then you have to update the software in the chip, right? So you have to build this whole loop and stuff. So that's one problem, and nobody thinks of building this loop, right? I mean, people know about it. So interfacing with the physical world is a real number 2 problem is people want accuracy, which I understand. Because if your accuracy drops to 50%, you might as well toss a coin, right? So how do you get 90% accuracy in a real tiny model? Big problem, right? So what people do is they'll say, oh, look, I'm only burning a microwatt. I dropped 5% accuracy here, 5% accuracy here, but look, I'm only... The problem is accuracy is a primary driver. And there is research going on in terms of how to change AI, how to improve AI models to reduce size. I mean, but there are 2 axes, right? Most of the interest now is making bigger and bigger AI models to do things, not in reducing.
And communication, costs nothing. So I always used to think in, parsing it in 3 buckets. One is for living in the physical world is one bucket is sensing, right? So whatever power is needed to sense, you sense. Then if there is local signal processing, that's another bucket. And the third is you have to analyze or conclude or come to some directive based on what you just sensed. And if that communication, even of sending all the raw data out to the cloud, is ridiculously cheap, there's nothing left in the dumb device to do or optimize because it costs nothing to get it up there. So you always have to be looking at where does it make sense to do what in anything.
Yes, Sanjay, that's absolutely right. So the edge guys, I mean, I've been part of this. So we always give the spiel like, privacy. You don't need to send your data to the cloud. Number 2, battery powered, because communication costs a lot of energy. But, then you start putting and all these segments, and you can see it drops, 0.1, 0.1, 0.1, and soon you're at 0.001 of the app space. So far, I still don't see, I'm working at Renesas, we still sell some of this stuff. I still don't see a big uptick in edge devices.
Example, the warfare in Ukraine, that to me seems to be a place where, so to speak, intelligence at the edge is showing remarkable results.
But again, what is it at the edge? It's not at the edge device, right? I mean, what's the edge device doing? You take all the data, analyze it in the cloud, and act on it. So what is the reason to do it at the edge? I mean, eventually autonomous soldiers, for example, of course you have to do it at the edge, right? Or drones.
But some aspect is, latency, right?
Latency is another thing they say, and which is true. But again, if I, for example, a motor, I'm sensing that the motor is doing something bad and I want to shut it, right? Latency-wise, sure, I can shut it. But do I really want to shut it without a human intervention? I mean, this is part of some big process chain, right? I just can't, I have this chip which just goes, oh, something bad has happened, I'm going to just shut it. But having said that, automotive is one of the biggest edge AI applications. So not to forget that. So yes, edge AI is playing a big role in automotive.
But I guess one question is, I mean, is there low power needed? I don't think automotive needs low power.
Yeah, so it doesn't need low power. The low power axis is not stressed, but it is edge.
Yeah. No, it is futuristic. It's going to take a lot of time to mature, which is why I was saying, stuff you do now might come in later. But imagine every lamppost is similarly, active in some way. Now, the kind of stuff you can do with distributed networks like this, communicating locally, that is what we have been drooling over for decades now. That when we can make that happen, that could be quite that could be quite impactful.
I think my worry is you'll run out of drool before that happens. But that's just
take time.
Yeah. So
I wanted to come to some other point about the efficiency thing that Rohit had raised, because I think it's actually pretty remarkable how, I don't know if anyone else wants to raise something great, otherwise I can go to this efficiency thing. So Rohit, my point is simply this: efficiency, as we are now seeing, is highly overrated. All the stuff that we are seeing with the AI large language model stuff, how mind-bogglingly inefficient it is. But it's by going to that level of abstraction where we got those closed loops, we are able to test on massive amounts of data. I'm developing stuff for investors on Wall Street today, and I'm using stuff that's been trained on everything on the stupid internet. How stupid is this? How inefficient it is. But we got to a level where stuff like what I'm trying to do is feasible, and stuff like lots of other people are trying to do is feasible. So this, to me, was the lesson of the last 15 years, is in some ways turning upside down our standard view of how science progresses, what is important in engineering, and so on. I'm not claiming that this will keep going on. I'm just saying we went through a phase where, in fact, efficiency would have killed us if that had been a primary focus for us.
Vas, just to add to your point, in terms of coding, today we are producing millions of coders who are terrible, frankly. Okay, they don't understand all the algorithms and the most efficient way to implement stuff. But they implement stuff, and guess what? The processors are fast and they run and things happen, right? So for more productivity, we traded off efficiency. So that's another way of looking at efficiency.
There was a question that was not brought up. Somebody had posted on chat about quantum computing and where it is and where it is going.
Yes, that's a very good question. And the answer is, I frankly don't know. I mean, I've seen some progress on it, but it seems to be very far away from anything practical. So one thing that we are being told in terms of security and stuff is right now to increase our security IP by another couple of factors, so that if quantum comes in, we are a bit better prepared. That's about all I know. Vas, do you know more?
No, what I can do, I don't know sort of what are the ground rules for this group. I have a good buddy of mine from IBM Research who's a top guy in quantum at NVIDIA. How he got there is a whole different story. I can ask him to give a talk to this group if there is interest in that space.
Yeah, that would be great. I think, no, there are no ground rules. I mean, we're just going.
Great, but one of the things, I mean, for encryption and stuff, there are main issue in quantum is hardware. Let's face it. And getting something that is stable and can entangle over large number of qubits. People like IBM and Google, etc., are claiming they're making progress, and I haven't looked into it in a few years since I retired, but hardware remains the main challenge. So it's, the software piece is not the hard piece, but if people are doing something in terms of stability of the hardware, because it's very easy to make unstable qubits where you lose all the quantum benefits from if you lose all the large scale entanglement. But I'd love to listen to the guy at IBM and see what he's saying, because last time I looked at them, they needed, 9 error correction bits to make one stable qubit. So scaling certainly becomes a problem. But you don't need, for quantum supremacy, you don't need that many qubits. So maybe that's the argument to make. But we should get that guy in.
Yeah, I would
the
love to hear it.
The question I would have about that is, would the chip design be fundamentally different, or would it operate on the same chips and the architecture is different?
No, it would be totally different.
Totally different.
So who's manufacturing those chips? There must be somebody.
Who's designing? Who's designing the chips, first of all? The material. This is not, you're not coming in with a supply chain of zone refined silicon that you can then say, okay, I'm going to take a 12-inch cut and start my stuff on it. Even the material systems people are working on are extremely different. So it's at a very different stage than.
It's not even a chip today, I would say, Sap. It's not a chip. It's a big piece of.
It's a big refrigerator. It's a big
refrigerator. We are far away from.
And don't think of it as a refrigerator size. I mean, this is it's running close to absolute 0 Kelvin, temperature. So.
So Saurabh, if you want to be shocked, think about what Gopal was saying. 200,000 centigrade, way beyond the surface of the sun. And now we're talking 0 centigrade. It's like, that's where
zero Kelvin.
0 centigrade.
0 Kelvin.
Yeah. So Vijay, it'll be great. Would you speak with him? And see, what we are doing currently is we are doing one talk a month. But what we can do is we can squeeze him in and do this, do 2 talks in a month if whatever date is convenient to him. Yeah.
Let me get back to you. Just a few quick words on this, Sanjay. So 2015-16, I was a bit involved at the quantum side in IBM research, because for the obvious point, we had a whole bunch of hardware guys doing stuff. What the heck is the programming model? How are you actually going to work with this stuff? And I was skeptical, then I'm still skeptical that this will actually become real. But even more important, therefore, to find someone who can speak coherently, someone that I trust, who can speak coherently, what are the technical issues?
And somebody who's up to date, right? Because I personally ran a quantum computing group at Nokia Bell Labs when I was there. But, it's still, and the programming models, as are very different in terms of even the gate operations, right? You had to create Hadamard gates, and it's different, and that's why. But I used to talk to people like Microsoft, and who were, of course, interested in the progress we were making. But the thing I've got the most laugh out of was they're saying, we have our visual suite, programming suite ready for quantum computing. All we need is the hardware.
Yeah, I saw that. I thought that was hilarious. Yeah. Yeah.
All right, great. Gopal, people, the comments here, people have absolutely loved what you presented here today, and the style in which you presented it, and your story with Infi was just fabulous. So I wish you talk about it much more broadly than just to us small people here. Thank you so much.
We were customers of Infi, and because in being in the optics business, so it was a terrific company because of the speed was really, and lasers and stuff. It was quite phenomenal. So that we're always proud. I said, I know the founder.
Awesome.
That's great. It's another really satisfied customer.
No, but really,
Gopal,
really fantastic talk and slides. So when you will send out the slides?
I'll send out the slides, and I'll send out the quiz also.
Yeah.
So I hope that the quiz the slides can't be referenced for the quiz.
Oh, you can. The quiz is
open
book.
It's an open book, Saf.
It's an open book, man.
Sanjay,
at this age, I don't like closed book.
Topoing is allowed,
Gopal.
Fantastic, Gopal. This was really, really nice.
Yeah, great talk.
Thank you so much.
Great.
I said that about Bass's talk, but this time I really mean it.
So who was forcing you to talk like that last time?
Yeah, just Bass's talk, but I loved it, Gopal. This is great.
This is wonderful.
Thank you.
Yeah.
Thank you.
Guys are welcome.
Really nice.
And let me announce the next talk here. I'll be announcing it on the groups. So it is V. Balaji who's going to be talking about climate modeling, what we know and how we know it. And I'm going to be, so V. Balaji is from the 1981 batch, Tall Balaji. And so we'll hear from him next month, 21st October, Saturday, same time.
I don't know if he was on this time, but
Yeah, he was not. I saw.
He's okay because I sicked him onto you. You know, he was first the guy who told me about chip wars and says it's a must read, but I think he's doing something more on it. And I said Gopal is the guy you need to talk to, not me.
So while we're on the subject of Gopal, right? So I have a story from many, many years ago. I think Gopal will remember. So Gopal and I, that's Gopal Raghavan, Gopal Pathrajan and myself were driving back from California back to Chicago in this Chevy Camaro. It was, I think, 66 Chevy Camaro.
You came to Minnesota. You came to Minnesota.
Yeah. Yeah, but we
don't forget South Dakota.
Yeah, Rapid City, man.
Yeah, exactly. We stopped at the Grand Tetons. We camped there, and we were climbing the Grand Tetons. And believe it or not, rubber chapels. We were in rubber chapels climbing the Grand Tetons.
Summer, I hope. Summer.
You mean the Hawaii chapels of IITK, huh?
Yeah. It was, and I think one of them was broken, tied together with string, and of course,
my chapel broke. My chapel broke when I was climbing, and I had to do it without my chapel. I did it on bare feet, but
that's quite a climb.
Yeah.
I mean,
that's impressive.
Yeah. Actually, we were in Yellowstone just last week, and I was telling my wife about the same story, Murli.
So there used to be two colors for the Hawaii chapel, the fawn and the blue. Which one were you wearing?
Blue, man, blue, always blue.
But I think usually one breaks and you end up with one of each. So.
Yeah.
Safety pins were used to hold up.
Safety pins. I would like to have seen the one with the string.
Safety pins, you know. Yeah.
Not the Gangu Mochi type.
I think one of these days I'll make a quiz on IIT, our life there, and send it to you guys. You guys can respond. Let's see how much you remember.
Why don't you write a crossword on that with clues, and that'll be fun.
Yeah, I can try that.
We can do a spelling bee with only IITK words allowed.
Okay, Vijay, you do that.
A couple of days ago, I had one which had many of the Gandu and.
I know. We'll do one of those.
Okay.
Yeah.
All right.
Thanks for giving me an opportunity to follow.
Thank you.
I was
awesome. Happy to.
Yeah, thanks Saurabh and Kushro for organizing.
Thank you, guys.
Thank you, Saurabh.
Thank you, Saurabh.
And guys, if you have any suggestions about who might be good speakers, do let me know, because I do contact them. It is just that we have many speakers already lined up. I don't want to disclose up ahead which one is coming next until the previous talk is over. But we have a number of speakers now for the next 6 months. But I do want to know other people's names and what they've done to make them really suitable for more interesting discussion like these ones. So do let me know. Huh?
Thank you.
And Vas, of course, my statement was in jest to make.
Vas has to be credited.
It wasn't
with
as good as Gopal's. No,
no, but Vas has to be credited with having started this whole series, because it was his talk. He got excited about it, and then he said, "Hey, we can do a series of this."
Sure. Yeah.
So thank you, guys. Bye.
Thank you all. Talk to you soon.
Appreciate it.
Bye.
Bye.